the perfect emoji for the last day of classes is that little guy. He's happy, sad. I always use, or that's always how I feel. I don't know if I always use that emoji, but it's our last class today. Is this anyone's very last class of the term? Or do you have more classes after this? It's my last class of the term. Sad face. All right. I hope you guys don't have classes later today. Uh-oh, you do. This is just one step closer though. Feels good. Yeah, you're like knocking them down as you go. And then summertime. Yeah, that's how I always felt. Okay, yeah. Okay, so what I've decided to do is, because a lot of what was left in chapter 7 is a little bit beyond our assumed knowledge level. Now you might be comfortable with working with matrices and stuff like that, but I don't think that I can assume that you are. And so I've decided to give us kind of a break and just wrap up K-means clustering, introduce hierarchical clustering, but just kind of briefly, because ultimately in the workplace, you're going to be working with probably K-means clustering, and that's sufficient. Okay, so and then everything else is just kind of gravy. And once you have one under control, then you can tackle another one. So really what I'm trying to say is I've cut down our material, and for a nice breezy home stretch for this course. Okay, so our last class, there was something I wanted to do. Our final's not for a while yet, so you can expect, you know, some sort of announcement, or I don't know, closer to, but like I said last day, test 1, test 2, covered all the ground, and then the assignment for chapter 7. No, you can put those all together and those can be your practice exam. I could put them together for you, I guess, and that would be your practice exam. But no, those will be good practice, right? All right, so for a little bit of review, we were talking about, well, we talked about PCA, principal component analysis, and for me, it's a little bit trickier to wrap my head around. Oh yeah, so for the labs, I could, but there's no lab questions on the final. So I could, if there's anything in particular. I think I have solutions to all of them. Some of them are in Moodle, right? So they're gonna give you the solutions, but K-means clustering is on the final, yeah. Okay, sounds good. Yeah, I'll see what I can do about those solutions. Yeah. There'll probably be different numbers in my solution, but it'll work. Okay. All right. So awesome. I should write that down before I, you know, last day of classes, get excited. No, that's like every day for me. If I don't write it down, even if I write it down, I keep forgetting. Solutions for labs. No practice final. You can make your own practice final. Well, I guess it's a ways off. We'll see. Okay, so for review, oh yeah, we talked about principal component analysis. PCA, which assigns a weighting to each of the predictors, right? And then that generates a new predictor, okay, which we do for all of the existing predictors. And that's where it starts to sound like, well, what's the point of that? If I'm trying to reduce the number of predictors, which is what I'm doing, right? Then what's the point of generating all the same number of predictors that are just different from my originals? Well, because later on, what I can do is I can just take the first 4 principal components, or maybe the first 5 principal components, and all of a sudden, all those components have pieces of information from all the previous predictors. Even if we had like 20 predictors, right? If we were able to get a lot of the information from the first 5 principal components, that's a good thing, right? Then I've taken and it's called dimension reduction, right? Where I've reduced the number of predictors to a more reasonable set. Okay, so principal component analysis is typically used for dimension reduction. Right, which means reducing the number of predictors right? And so remember what it does is it generates these linear combinations of all the predictors, right? So each principal component is a linear combination of all of the original predictors. I'm going to add weighted because of course that's important, is a weighted linear combination of all the original predictors. Okay. And so we generate principal components for each existing predictor, right? We generate principal components for each original predictor, right? So the same number of predictors, right? But then we only use as many as describe some desired amount of variability. Okay. But then we only retain, right? So keep, so right, we only retain as many as are needed to describe some desired level of variability. Retain the number required to explain some desired level of variability, level or percentage of variability. So that's kind of cool, right? So we do go through all that work, but then each principal component right, has information from all of the predictors, right? And it has the weights, right, trying to kind of stretch out and cover as much variability as it can. So that's really cool, right? It's a little bit hard to explain to a client, right? Whereas K-means clustering, I think, is maybe a little bit easier to explain. At least we all have a pretty good idea of, if we're given a graph, right, and I pick a point and then there are some points close to it, right? And so K-means clustering is the next one. So K-means clustering is also typically used, maybe not to reduce the number of predictors, but to create another predictor variable where you can use the cluster as a predictor, right? And so often used to generate a new predictor variable, right? But use it, and I'll say using existing predictors. It's possible then that my cluster that I've generated, right, maybe it carries some of that same information. And so then I'm able to do some dimension reduction by analyzing, okay, well, if I introduce these clusters, do I really need to have, you know, the salary and the age range and all these things that maybe go into making the cluster? So let's just leave it as it's often used to generate a new predictor variable, right? And that's based off of existing predictors, right? And then sometimes we're able to reduce the number of predictors because a lot of it is captured by the clusters. Okay. I will say this. So remember last day I said, oh, I don't want to commit for sure, but I feel like PCA and K-means is mostly for numerical data, and that is true. So I'm willing to commit to that now. Okay, so PCA and K-means clustering is mostly applicable to numeric predictors, okay? So to numeric data. So even if you have categorical variables, such as a binary variable 0, 1, so those are numbers, but they're not numeric data, okay? And so usually we focus on numeric data. Okay? And so PCA and K-means clustering is mostly used for numeric data. Okay. In theory, you could apply it to categorical data, but it's not really something that you do, right? There are other techniques that you could do there, and the very last section of the textbook goes through and talks about, okay, what if I have mixed data, right? What if I have some numeric data and I have some categorical data, even if it's coded, you know, in order, and even if it's numerical order data, right? Or if it's binary, right? The one-hot encoders, those aren't truly numeric, right? Those are categorical variables recoded as numbers, right? But in their heart of hearts, they're still categorical, right? And so you don't want to use those for PCA and K-means because they kind of trip things up. They kind of mess things up. There are ways to deal with that, but I just feel like that's maybe beyond the scope of this course. And so I'm parking lotting it, I'm ignoring it. But I do encourage you to check out that last section. I think it's scaling and categorical variables in the textbook. Okay. So it's mostly used for numeric data, and that's because categorical data can sometimes affect the results. Okay. Categorical data can affect the results. Right, unintentionally, but still. Okay. Good. So K-means clustering, right? If we think about how we approached it, we said, okay, I'm going to pick some number of for K, right? However many clusters I want. And what we didn't get to talk about is how do we decide what K should be? And this is really one of those things where we remember that data science is just as much of a dance as it is scientific. Okay, and so you really have to kind of be flexible, and maybe your client has some number of clusters in mind, right? And maybe that's not the ideal number of clusters, but if they're paying you to find these clusters, if they say we want 3 clusters, right, you're going to do that. That's fine, right? Or if there's some reasonable value for the number of clusters that you want to find, right? Maybe the optimal number of clusters is 18, but maybe that's out of reach for programming reasons, maybe for call center reasons, right? Maybe that's too many clusters, right? Imagine you're developing training information for 18 different clusters when a lot of those clusters are going to be kind of similar, right? So then maybe you're better off using 5 or something like that, right? So even though there are, you know, kind of scientific ways of deciding K, so that elbow graph, for example, right, you can look at all the different Ks, and then where the variability starts to plateau, that's the one that you pick, kind of where you're not really gaining any more variability captured. That's the K that you choose, but maybe that's not reasonable, right? And so, let's say choosing K, right? Statistical methods exist. Statistical methods exist. And I think the textbook even introduces something called the gap method or something. Of course, we could find, we could say, okay, once the variability does not exceed some gap, then we stop, right? There's all kinds of weird things that we could do, kind of fun things, mathematical things that we could do. So statistical methods exist, right? The elbow graph, which says pick K that where the elbow of the graph is. Pick the K closest to the elbow of the graph. Right? So there are kind of ways that we can do it. Okay. And there's an elbow graph in the textbook, but I also happen to know that you've seen them in 300, so that's why I'm kind of sneaking past it, right? But it draws the number of Ks and the amount of variability that's captured, right, at each K. And once you start seeing a decrease in the amount of variability that's captured, that's the one that you would pick. Okay, so here, statistical methods exist, but often your client will be the one to dictate how many clusters are reasonable or necessary. But often your client right? Or some other force, let's say, right? Or some other kind of, I don't know, motivator, right? Maybe you only want to deal with 4 clusters, right? Maybe you're that needy person, not your client, right? And so, or some, so often your client or some other reason, but often your client will have an idea of how many clusters are reasonable / necessary. Okay. And I guess I finished the review somewhere around here. Sneak that in there somewhere, sorry. And then I just kind of snowballed it. I guess that's how a review works, but still. Okay. Okay. So there are ways that we can choose K, but often there are other factors that we need to take into account. And so then we don't really have as much freedom as we feel like we might have. And that's fine, that's okay. Okay. I can't remember if we talked about the cluster sizes. Did we? Okay. So I did say that most often the sizes of the clusters will not be the same, right? And that's totally fine, right? Because the main goal is to find the clusters that are best separated, okay? But there's a but, right? If you're finding that some clusters are a lot smaller or a lot bigger, right? And so they're not roughly equal, right? That's something that you might want to look into, right? Because how are small clusters generated? They're generated by these extreme observations that are lumped together, right? And so they're very separate from the data, right? So maybe that's a group that you want to tease out of your data set. Right. And so that's something that you would want to look at. Right. And so it gives us an opportunity to say, oh, okay, well, that actually looks, why is this cluster so small? Right. Compared to the other clusters, which are kind of happening and normal. I don't want to say normal, right? That means normal distribution typically, but kind of happening over here, right? How do I not say normally? Anyways, so, right, once we have our clusters, it is a good idea to consider the sample sizes in each cluster. It is a good idea to consider the sample sizes in each cluster. Okay. It's totally fine. We do not expect the cluster sizes to be the same. We do not expect the cluster sizes to be the same. But we do expect them to kind of be on the same scale, right? Or on a similar scale even, right? We're pretty flexible, right? But we do expect them to be on a similar scale. Okay. So if we find that one group is kind of unusually small, typically it's unusually small, and then unusually big is not that bad, okay? But if we find a cluster that is unusually small, right, that can be indicative of a cluster of outliers that need to be examined, right? So if we find, okay, that's a weird group, what are they doing over here, right? Those clusters are easy to find, but also they don't really reach out and grab observations from down here, right? They kind of stick here, and so that's what makes them small, right? So if we find the cluster that's unusually small, it is often, notice how I'm constantly using words like often, likely, right? Probably, right? It's because we want to be really vague, because there's always scenarios where, okay, no, that just happened, right? But usually, right, we're in statistics especially, right? We're talking about, okay, what usually happens here, right? And so it is often because it consists of outliers, that should be examined. Maybe your conclusion is, okay, I've looked at those outliers, they seem fine, they seem reasonable, and you know, one option is to pull them out of the data set and analyze them separately, right? But that all comes with practice, okay? So for now, let's just say, okay, we're gonna examine those. How do I do that? That's for another course, right? But usually you can analyze the data with that extreme cluster in there, with it removed, right? Do I see any changes? If I don't see any changes, then what can I do? Well, then I can just leave them in there, right? Then there's no harm in leaving them in there. But if I'm getting drastically different results with those outlier cluster in versus out, then I have a decision to make, right? And that's not always easy, but that's the job, okay? All right. All right. So the last thing that I want to talk about is hierarchical clustering, which I find hard to say and hard to write. So here we go. So the last clustering technique that we're going to consider is hierarchical clustering. Now, the textbook does also introduce something called model-based clustering, but I'm skipping it because it requires kind of some matrix knowledge, and also we haven't talked about the multivariate normal distribution, etc. So it just felt a little out of reach for us, and that's fine. That's fine. The last clustering technique I want to introduce is hierarchical. So hard to spell. Hierarchical and say clustering. Okay. Here's where I'm going to say that the text. So if you read the textbook, then you might be sighing a sigh of relief here, saying, okay, we're not actually going to be tested on that. That's great. But I do encourage you to flip through it and just kind of see that, okay, it's not that bad, but if we don't know about matrices and stuff like that and how we talk about those, then it gets a little weird. Okay, so is hierarchical clustering. The textbook also introduces model-based clustering. But, and this is what all teachers like to say, but I'm going to leave that for a later course. Pawn it off on someone else, probably Claude. Model-based clustering, but, and I'll put it in quotes here, we will leave it for another course. Every prof at the end of term. I feel like we always say that. Oh, that's for another course. And that's what I'm doing now. Okay. So let's see here. Hierarchical clustering. The idea is kind of reverse of K-means clustering. And of course, they've thought of everything, right? So, so K-means clustering said, okay, if I want 4 clusters, then I randomly divvy up everyone into 4 clusters, just randomly assign them to 4 clusters. And then those clusters are kind of massaged until there's no change and everyone is in their most similar clusters. Hierarchical clustering starts off where everyone is their own cluster and then clusters are merged, right? The least dissimilar clusters, and that's important that we don't say the most similar, it's the least dissimilar clusters are merged together until we reach some threshold. Okay. So hierarchical clustering says that each observation is initially considered its own cluster. Considered its own cluster. Well, so now instead of calling them observations, we're going to call them clusters, but initially a cluster is an observation, right? Then each, the clusters that are the least dissimilar are merged together. The clusters that are the least dissimilar. Okay, so that's going to be important, right? How do we measure? So now we have we have a pretty good idea of what happens now, right? Because we've talked about, okay, if I need to figure out the least dissimilar, of course, I need to have some dissimilarity metric, and there are lots to choose from, but I'm going to talk about 2 main ones. And then there's others in the textbook, but so then I need some way to figure out, okay, what is the cluster that is the least dissimilar to me? Okay, and then I go and I join that and I make my own cluster. Okay. The clusters that are the least dissimilar are merged into the same cluster. This continues until everyone is in a cluster. this continues until I want to say each observation is in a cluster, and it's possible for a cluster to have a size of 1, okay, until I think it's more than 1 observation. There was a special wording, but it's escaping me now. This continues until all observations are in clusters. Right. And there's some stopping algorithm. I know I'm reaching for my textbook right now, but I know I'm never going to find that very specific piece of text where it says, I think it's 1. So you can have clusters of 1, right? If they never merge with another cluster, that's fine. But I can't remember exactly, but that's the general idea. Okay. This means that we need to be able to measure dissimilarity between 2 clusters. Okay. The first dissimilarity measure is, I want to say, the complete linkage. The complete linkage says that, okay, I'm going to look at the furthest points. So the 2 points within a cluster that are the furthest apart from each other, right? And if I've maximized that distance, then I have that dissimilarity measure, right? That's how dissimilar these 2 things are. Now, if that maximum distance is not very much, then that's the least dissimilar, right? Whereas if I have the single linkage, which is the minimum, and of course there's the average linkage, and I think there's Ward's method, and there's tons of other methods, but we just need to have a grip on 2 or so, right? And then we can kind of take it from there. Of course, it's just a matter of altering some code in our R code or Python code, so it's not a big deal, but we need to know what they're doing, right? And what values, or what can we expect, right? And so we need to be able to measure dissimilarity between 2 clusters. And so we're going to start with the complete linkage. Which is the maximum distance between the observations furthest from each other. Between the observations furthest from each other. Okay, so what we can do is we can draw these clusters. I'm going to have cluster A, and I'm going to have cluster B, and then I'm going to have cluster C somewhere down here. I'm going to try to be kind of careful here, drawing my, so I've got my observations in here, and they don't necessarily have the same number of observations. And because I just drew these willy-nilly, right, then what I'm going to say is, okay, my dissimilarity measure is going to be, for a complete linkage, is the maximum distance between the observations that are furthest from each other. So let's say that these 2 observations are furthest from each other. And that's going to give me the complete linkage. Okay. And so those two observations are the furthest from each other. And this is my dissimilarity measure. Versus, okay, it's going to be this one and I don't know, maybe this one. It's not always the same point, right? Then this is my dissimilarity measure. I'm going to grab the formula that they gave because I don't have it off the top of my head here. The dissimilarity between A and B. So for example, A and B is, so in notation, what we're drawing here is the maximum distance between AI and BJ for all pairs IJ. Okay. If this is observation 1, then you're not going to, your computer is going to go ahead and find the distance between this point and this point and this point and this point, right? And then it moves on to this point and this point and this point and this point. But in the end, we only keep the maximum distance, okay? And then that gives us this dissimilarity measure. And the clusters that are the least dissimilar, so the smallest dissimilarity measure, are merged into the same cluster. Okay, so in this case, of course, this distance is a lot longer than the pink distance. So the green distance is a lot longer than the pink distance. So then A and B would be merged together and act as one cluster in the future. Right, C would stay its own cluster. As opposed to, and so now that you've seen it visually, and so now what if I give you the formula for the single linkage? Okay, the single linkage is now going to be the minimum distance between the observations that are closest to each other. So the single linkage is the minimum distance. I guess I've got it right here. Between the records in two clusters. And the distance or the dissimilarity between A and B is going to be the minimum distance between AI and BJ for all pairs IJ. Good. So there are other linkage or other methods. Other dissimilarity measures. Include average linkage. So take some average distance. That's fine. You're still finding all those distances. It's just whether you're using the minimum or the maximum. And then you could take the average. That's fine. The average linkage, or I had it here. I checked it so many times, or minimum variance, which we're not going to touch on. Okay, but those are some other dissimilarity measures. and they each have their own way of finding this dissimilarity, okay? All right, so let's see here. I feel like I had something I wanted to say here. That's okay. Oh yeah, got it. So the dissimilarity measure that you use could greatly impact what type of clustering you have, right? So whether you use, the first linkage, the complete linkage that we used or that we introduced, it tends to produce the most similar clusters, and that's a good thing, right? And so, right, whereas the single linkage is kind of, you know, oh, there's a close one in here, and maybe that's a cluster with a bunch of outliers, but you're just catching one outlier that's closer than the others, and then you go ahead and merge those together, and that's maybe not ideal, right? And so the clusters generated by each dissimilarity measure can be quite different from each other, right? So it might be nice to consider a couple of different, they're called linkages, right? So maybe maybe consider a couple and see how they're similar or maybe not similar, and then go from there, right? And so depending on what is reasonable with your data, right, maybe some clustering technique is more reasonable than others, but you won't know until you've generated all those clusters and you say, okay, well, yeah, it makes sense that this group of bankers, for example, they're in this group, whereas this group of clients or whatever, they're in this group. Okay, and so the clusters generated by each dissimilarity measure, as well as, so for hierarchical clustering, but also for K-means clustering or PCA if we wanted to take it that far, right? But let's focus on hierarchical. So the clusters generated by each dissimilarity measure can be quite different from each other. So it's a good idea to kind of check the results for as many as you can. So it is a good idea to check the clusters for a few different linkages, which I'm using instead of dissimilarity measures. Okay, good. So notice hierarchical clustering, we don't really specify, or we do not specify how many clusters we want. In fact, we just let it run till the end until everyone's in a cluster, either by themselves or with other observations. But what we get is this tree, and it's called a dendrogram, and I always spell it wrong for some reason. Today is like things I spell incorrectly and have a hard time saying. We can visualize the results of hierarchical clustering using a dendrogram. Make sure I spelled that right. Okay. And so notice that we haven't specified how many clusters we want. And so a benefit of a dendrogram is that we can visualize what the clusters would be if we cut it at some point. Now, I wish I had a dendrogram here that I could show you, but you've seen them. I know you have. I know you have in the textbook, if not in other courses. Okay, and so let's see here. I wish I could, I guess I could take a picture of this textbook, right? But really what it's gonna look like, and I never do a very good job of drawing stuff, but it kind of looks like maybe something like this. Something like that, right? And so it shows all the different clusters that we might have, right? And so if I cut it maybe at this point here, right, I would have 3 clusters. I would have this cluster, and then I would have this as all as one cluster. That's maybe not the best way to go because there's a lot of different clusters here, but if they're really small, then we just kind of shrink them up into one. Okay. And so here, right, from the dendrogram, oops. We can select the appropriate number of clusters. Right? So for example, if I cut it here, then I would have this cluster, and this cluster. Whereas if I cut it, I don't know, here, well, I would still have this cluster, and 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 this cluster. And so it depends on how many I want. And I find reading dendrograms, I know they're supposed to be like this amazing tool for visualizing it, but I find that they're very confusing. Sometimes often there's a lot of branches. So when do you cut it? For me personally, I just find that difficult. Okay, good. You won't believe it, but that's all I wanted to talk about today. Thought I would take more time, but hopefully you guys are okay with that. We can talk more, but it would be about model-based clustering, which I've already decided. No, we're not going to do. So all I want to say now is thank you so much for working so hard. It's been a pleasure having you in my class, and I hope everyone has a great summer, but also great final exams. If you have any questions, let me know. Otherwise, I'll stop this recording and see you soon.